Please introduce our next speaker. It's Shuli Shu from UC San Diego.
Thank you for the introduction, and you can hear me, right? All right. And thank you very much for the invitation. It's a great pleasure to speak here. So I never been to Oslo. I hope in the future I can actually visit in person. So this is a talk about Motivic stable homotopy groups of spheres. So I figured I should spend some time in the classical stable homotopy groups of spheres. So that's the plan. I'll spend, roughly speaking, 1/3 of time explaining some historical methods of computing stable stems classically, and then I will go to the Motivic case. All right. So stable homotopy groups of spheres are the kind of mathematical objects which are very easy to define, but very hard to compute with. So if you take base maps between spheres in dimension n plus k to k, and we model by homotopy, so these are the homotopy groups of spheres. And if we take the suspension enough, so we get into the stable range. So this is the stable pi n. It has nothing to do with k anymore. So this is usually referred to as the n stem. So these objects actually have a lot of connections to other subjects of mathematics, in particular differentiable manifolds. So this is the one of the reasons that a lot of people care about classical stable stems. So I'll list a few examples. So the work of Pondriakin tells us it classifies framed n manifolds up to framed cobordism. Framed here means it has a stable normal bundle on its framing. The work of Cavere and Milner tells us the stable pi n actually classifies, in a certain sense, smooth structures on the n spheres. And the work of Broder tells us the Cavere invariant problem, which is another problem in differentiable geometry, that when the Cavere invariant of a manifold is 0, 1 in dimension n, also correspond to a statement regarding the nth stable stems. So based on all the earlier work, a recent result by Gordon Wang and myself, we actually computed the stable 61st stem as a prime 2 is 0. And by the work of Cavere Milner, that tells us the 61 sphere has a unique smooth structure. And based on work of Cavere Milner, Broder, and Hugh Hopkins Ravenel, we actually show this is the last odd dimensional case. So the only odd dimensional spheres with a unique smooth structure are 1, 3, 5, and 61. And these proofs are done through computation of stable stems. Okay, so that's some motivation there. So how exactly do we compute these groups and what do we know about them? So Sarah told us these are always finite abelian groups when the stem is at least 1. So since we know a complete classification of finite abelian groups, so that means we can compute a prime at a time, then sum them all together. But there are more structures. So we can take the composite of two maps, and then they result in the sum of the dimensions. So that gives us a graded ring structure, and it's commutative in the graded sense. But there are more structures. So there are some higher products, namely matrix total brackets. So if you have 3 consecutive elements, and the pair of each pair of 2 of them are 0, then we can form a 3-fold total brackets, and similarly we can form some higher products. So these are the topological analog of massive products. So when we want to compute these groups, we would like to compute all these structures as much as possible, because they could tell us about the group structures in the end. So unstably, the first breakthrough is by Serre using the Serre spiral sequence and computed the unstable, the whole unstable range, the bigraded thing, and until it reaches us to the stable range, then up to, roughly speaking, the A stem. And then Toda used the EHP sequence, and Toda computed up to the 19 stem unstably. So if we care more about the stable groups, so 2 of the major methods are the Adams spectral sequence and as Adams-Novikov spectral sequence. So they both start from the X group over some half algebra or half algebroid, and it converges to the P primary part of the stable stems. So, so they're based on different cohomology series, and the Adams spiral sequence is based on the classical one, and the Adams-Novikov spiral sequence is based on the complex cobordism MU, or it's if we localize the P at the Brown-Peterson spectrum BP. Okay, so before I talk about actual computations, so here's a warning. So I think I should mention this in the beginning, so to give you a taste of the field. So this is usually referred as the Mahowald uncertainty principles. So the first Mahowald uncertainty principle was phrased by Doug Ravenel, which says that any spectral sequence converging to the homotopy groups of spheres with an E2 term then can be named using homological algebra. So Adams and Adams-Novikov are both examples like this, will be infinitely far from the actual answer. So what this means is that this problem of computing stable stems is not an algebraic problem in nature. So whatever method that give us a spectral sequence whose E2 page can be computed by algebra, by homological algebra, is not going to be the actual answer. There will be infinite many differentials in this spectral sequence. So we still have to deal with the differentials, but this problem itself is not an algebraic problem. So based on the experience I had with Mark Mahowald, so I proposed the second Mahowald uncertainty principles. So which says that any method that computes non-trivial differentials in such a spectral sequence will leave infinite many differentials undecided. So when I first started to get into this subject, I asked Mark Mahowald, what is the best method of computing stable stems? So Mahowald told me that there's no best method. You really have to combine everything you got to push forward the known range for maybe just a little bit. So that's a spirit that, well, there's not going to be just one method that computes all the differentials. So each method will reach some obstacle, and then people need to find out some new method and combine it all together to move forward. So that's the spirit of the second Mahowald uncertainty principle, that we always gonna need new methods. So having these things in mind, so one natural thing to consider is to compare the Adams spectral sequence and the Adams-Novikov spectral sequence. So here are some pictures. Well, they're both the X group of some half algebroid, and they converge to the same thing. So how do we compare them? Well, luckily we have one map, which is the Tom reduction map. So we have a map on the spectrum level from BP to H of P. So that gives us a map that preserves all the bigradings here and a naturality. Okay, so they converge to the same thing. So this method is useful in some situation, but not super useful in other situations. So for example, one thing we encounter all the time if we have two spiral sequences converging to the same thing is the jump off filtration phenomena. So what I mean by this is that if you have an element, homotopy class, which survives in both spectral sequences, but the elements in the beginning in the E2 pages that detects this homotopy class may have different filtrations. So when that happens, that tells us this map does not see the connection of these two arrangements. So that's not always a good thing. Well, it could be a good thing in some cases, I guess. So luckily, we have another connection, which is slightly more complicated, but it turns out to be very useful. So Hinz-Miller, in his thesis, he constructed a diagram of spectral sequences. So here is another gadget, and it's X over some other half algebroid. And it serves as the starting point of two other spectral sequences. One is the algebraic Novikov spectral sequence that comes from some powers of augmentation ideal of BP star, and it converges to the Adams-Novikov E2 page. And so there's also a Cartan-Ehrenberg spectral sequences that converges to the Adams E2 page. So having this Miller square in mind, it actually, so if you view this as a map, then for any homotopy class in the end, we can actually compare everything in the arrangement. So that gives us one more way of comparing things on the Adams side and on the Adams-Novikov side. So moreover, there is a very interesting phenomena, which is that the Cotton-Allenberg spectral sequences, it collapses at all primes. So what this means is that at all primes, if we start from the same arrangement, then there are two ways to go to the destination. One is the Cotton-Allenberg, then the Adams, or we could go the algebraic Novikov, then the Adams-Novikov. But at all primes, this spectral sequence has nothing happens here. So that means all the information in the Adams differentials that will happen partly in the algebraic Novikov and partly in the Adams-Novikov. So that means at all primes, the Adams-Novikov E2 page, if we can choose to start from here, is always going to be better than the Adams because half of the job is already done. So that's not going to be the case at the prime 2, but at all primes, if one can choose to start from the Novikov E2 page, so that's the place we should start with. So moreover, Hans-Miller developed a technology, a technique, I guess, that help us to determine Adams D2 differentials from algebraic Novikov D2 differentials. So I should mention that the above two spectral sequences are more topological in nature. So they start from some algebra, the X group of some half algebroid, then they converge to stable stems. And the lower two spectral sequences, they're more algebraic in nature. So they start from some X groups, they converge to some X groups. So in theory, the lower two spectral sequences can be computed by a computer program, say, within any reasonable range. So this theorem of Hans-Miller is actually very powerful because it tells us how to compute Adams D2 differentials, which are a priori topological in nature from some purely algebraic data. And based on this technology, Hans-Miller proved what is now called the the telescope conjecture at height 1 at odd primes. So later on in my talk, I'm going to give another proof of this theorem and also generalize to higher lengths, not just the D2, using Motivic homotopy theory. Okay, so having that being said, so what is the state of the art? So what is the knowledge for Stemwise computations? So at p equals 3, by work of Nakamura, Tangara, and Doug Rabnow, so we know this around 108 stem. And for p equals to 5, in the Green Book, Doug computed around 1,000 stem. So these two numbers looks very different. But if you think about it, they're both about p cubed times 2p minus 2. So in this sense, they're actually, we know actually around the same range. So, but if we plug in p equals to 2, this number is as small as 16. So in that sense, so at prime 2, we actually know a larger range of stable stems now. Okay, so what about prime 2? So as I mentioned, at all primes, the Adams-Novikov is a more efficient tool. And at prime 2, the Adams spectral sequence turns out to be more useful nowadays. So for any spectral sequence, such as the Adams spectral sequence, there's always 3 problems to ask. The first problem is, so where do we start? As in, how do we compute the E2 page? So how do we compute this X group? The second question is, how do we solve all the differentials? So how do we compute all the non-zero differentials? And the last problem is that, how do we solve the extension problems? Namely, how do we get from the infinity page the thing we actually wanted to compute? So there are extension problems over there. So historically, the first question, as in how do we compute the E2 page, was answered by Peter May in his thesis. So Peter May constructed another spectral sequence, which is a trigraded one that converts to the Adams E2 page. And Peter May computed this into a large range, and then he deduced the Adams differentials from Toda's computation and used the product structure and deduced even more Adams differentials. And in the end, he knows the stable stems up to the 28th stem as a prime 2. And all primes, he knows more than that. So nowadays, of course, we have all kinds of computer programs by, for example, by Bob Brunner, Chris Nassau, and a lot of others. So we can now compute the X group into much larger range, say 200 stems or so. So computing the E2 page is not going to be problem anymore. So the hard part is to compute the differentials as suggested by the Mahowald's uncertainty principles. So computing Adams differentials are really hard. So then by work of Barrett, Mahowald, Tangara, so they computed up to the 45 stem. So they were playing with the Moss theorem, which connects massive products in algebra and total brackets in homotopy. And moreover, Mahowald has this trick that he can use certain finite spectrum, certain finite CW complexes, and translate problems of computing differentials into solving extension problems. So combining all these kind of ad hoc methods, so they were able to compute up to the 45 step. And that's about, so this is in the 70s. So this is about our knowledge for a while. Then a more recent breakthrough is due to Dan Isaacson. So that's where the Motivic method comes in. So in 2004, Dan Isaacson uses the Motivic Adams spectral sequence over the complex numbers and computed the Motivic stable stems up to the 59 stem, and then also computed the classical stable stems up to the 59 stem. So I should also mention that during this long gaps in several decades, there are some also progress by Kochman using an entire different method, but it turns out that method have several errors and is not very compatible with other methods. But Dan Isaacson's computation up to the 59 stem is very concrete and solid. But he, again, got stuck there at 60. So in 2015, Gordon Wang and myself, we developed another purely classical method, which we call the RP infinity method. So we computed two more stems, 60 and 61. So that has the geometric application I mentioned in the beginning. But very soonly, the three of us realized together, there's another method in the Motivic homotopy theory, which is entirely very different from the method Dan had, which I will explain a little bit, the difference. And we call this the Motivic Tower method. So tau here can be viewed as a parameter of the deformation of the cellular Motivic homotopy category over C. And this allows us to compute up to the 90 stem, and it is still ongoing. So, well, okay, so I've been talking about spectral sequences. Here's a chart, a picture of what that looks like. So this is the E2 page of the classical Adams spectral sequence. So I can zoom in to show you this. So for those who are not familiar with a chart like this, so let me explain a little bit. So each dot here represents a Z-mod 2. So the whole spectral sequence is a vector space over F2. So each dot is a Z-mod 2. And we see some lines here that represents certain product structure. So each column here will goes to the homotopy groups. So for example, on the first column, there's only one dot. So that means pi1 is Z-mod 2. And the second column, there's only one dot. So that means pi2 is Z-mod 2. And the third column, there are three dots, but they're connected by this line segment. So instead of 3 copies of Z-mod 2, that corresponds to certain extensions. So this is actually a Z-mod 8. Pi4, pi5 are 0, pi6 is Z-mod 2, pi7 is Z-mod 16, pi8 is Z-mod 2 plus Z-mod 2, and so forth. So that's the beginning, and there's no room for differentials really. So later on, we start to encounter differentials. These are the lines with a negative scope. So what that really means is in the infinite page, the source and the target will cancel each other and will not contribute anything to the homotopy groups. So you will start to see a lot of differentials like that. And later on, and the pattern will become more and more complicated and so forth. So that's basically what we have in here. You will start to see multiple dots in a certain, within 1 by degree, and the names for them are kind of random. We started with, let me go back, with H stands for half invariant, and we started using element C, D with a subscript if they fall into some family, and E and F. And then later on, we run out of letters. So we start to use capital letters, and then when like capital C, capital D, and then we run out of letters again, we start to use something like X77,7, which just means the dot in stem 77 and filtration 7, and so forth. So it seems very complicated, but there are many patterns we can also see. So this is roughly speaking the range we had. So the range of Saratoga, May, Berman, Hopper, Tangara, and so forth. And this very narrow column is the result Gordon Wang and I had for 60 and 61. And now we're investigating in here, and there's only a few uncertainties we didn't know of. So it sounds like we only less than double the range, but the possibilities of differentials, the growth is exponential. So, so in that sense, we actually know a lot more than we know before. And this new Motivic method, we can also easily compute the known range without much effort. So, and this is the infinite page, meaning that this is actually homotopy groups. You see a big gap in here, and of course in here, and along the edge. So that's the K1 local sphere, or the real-body periodicity related stuff. It is very periodic, and the gap is predicted by chromatic homotopy theory. And there, so if you have this chart up to say range stem 1000, we should see probably clearly another layer, which corresponds to the second layer in chromatic homotopy theory. So which is about different periodicities in homotopy groups. And the 61 dimensional result just saying that there's no dot left in the 61st column in the infinity page of the Adams sphere sequences. Okay, so so of course we didn't compute all differentials up to 90 stem. So up to the value of 6 differentials, we know the complete infinite page. So only a handful. And with ongoing work with Birkeland, we have known a few more. So this is actually expected that we have left a few differentials behind. I think the first differential as in dimension that we don't know the answer now is around the 82, 83 stem. So this is okay because this does not violate the Mahowald uncertainty principles. So there's no one method that just compute everything. And we have already actually combined with other methods we know of. Okay, so that's a quick review of the classical computation of stable stems. So next, I'd like to go really into the Motivic work, which is what this conference is about. So I like to say that comparing to the classical literature knowledge, I'm not that familiar with everything motivically, especially when it's not cellular. So I like to apologize in advance if I have I didn't mention enough significant results. I'll credit to the wrong people who have done the corresponding work. So let me first start with the cellular category. The cellular category is generated by 2 types of spheres. So we have the simplicial sphere as 1,0, and we also have GM as 1,1. So we smash them together, we get P1, and we go from the Motivic space to spectrum. And I'm going to use the Motivic notation 1 as the Motivic sphere spectrum. So HFP will be my Motivic MAP and Maclaurin spectrum, which is also a cellular object. And any Adams type spare sequence computation will have some convergence problem that converts to certain P completion of the sphere spectrum. So my 1 hat will be the HFP complete sphere. Sometimes it has the same homotopy groups as the P complete sphere, but I'm not going to say this details very distinction like them very well. So this is the right object that the Adams spare sequence converts to. So, but a warning here is that classically the homotopy groups of the P complete sphere is the same thing as the homotopy groups of spheres that we take the algebraic P completion. But motivically, that's not the case. So therefore, any Adams type spare sequence just converts to the homotopy groups of a P complete sphere, not the other way around. And this is the Motivic stable stems. Okay, so the Motivic situation is much more complicated than the classical stable stems. So first of all, there are 2 gradings. So therefore, we shouldn't be just saying which stem it is, because there's the stem, there's also the motivic weight. And the second thing make it much more complicated is that for any field K, there's going to be motivic stable stems. So when we talk about computing stable stems motivically, we should say which field we're computing it over. So here's my knowledge about what's known now. So I might very well miss some major results. Please let me know. I'll give me a comment in the chat. So there are basically two directions of where these results go. So one direction is the result is for a general field, for an arbitrary field. So first work is my Morel, which says that pi n comma n of the sphere spectrum can be written in terms of the Mueller weight K groups. So or this is called the Mueller weight zero stem or the zero line. Then a more recent result by Rodix, Spitzbeck, and Ossphere that computes pi n plus 1 comma n of the sphere spectrum. Again, it's for an arbitrary field when the characteristic is not 2, and in terms of the summation Mueller K groups. So these results are general enough, and it computes for any field. So another direction of these computations, so these are like a totally different method, and that's not going to be the topic of this talk. So the slide spare sequence will play a major role in this work. So another direction is more compatible with what I mentioned in the classical case, which is the use of the Adams, Motivic Adams spectral sequence. So, and that only computes some P completed sphere and is very field specific. So the earlier work I mentioned, where we extend the classical stable stems, which also we also extended the C-motivic stable stems. So we actually know up to a few differentials, of course. For the first grading, the stems, we know everything up to 90 and for all the weights. And this is, I should say, the two completed sphere and over a field C. So the range is much larger than two previous results, but it's only for the two primary and only for the field C. So, and for the field R, there are recent results by Beaumont and Isaacson, and probably also Guillou, which they computed the first 11 Mueller weight stem, as in the difference, for the two complete sphere. And I think they now actually have a larger range than this one. And also work by Glynn Wilson and Wilson Ossphere when K is a finite field. So at weight 0, I think Wilson computed at all primes for s smaller or equals to 18. And at prime 2, Wilson and Ossphere computed for s depending on the congruence of the field, and they computed up to 18 or 20 for this field. So that's basically my knowledge for the state of the art for motivic stable stems. So my talk will be mostly focusing on the Adams spiral sequence way, and is field specific, and the goal is to get it into a larger range. Okay, so now let me explain how the motivic world helps with the classical computation and result in a large range computation over C. Okay, so the upshot is that we can view the cellular motivic stable homotopy category over C as a deformation using the parameter called Chow. And here it is. So first of all, C has a close connection to the classical world because there is this Betty realization for any variety over C. We can take the C points and get us a topological space. And we can extend that to the spectrum level all the way there. So we know the homology for point. This is due to Wolski. This is FP adding tau, where tau is this element in degree 0, -1. And it turns out this tau can be realized as a map between spheres, or between the completed spheres, like that. It does not exist as a map between the uncompleted spheres. So this is really a localized phenomenon in some sense. And this element tau, when you take the Beatty realization, it goes to 1 classically. So a major result by studying the motivic Adams spiral sequence by Degger and Isaacson is that if you're looking at the cellular category, and if we invert tau, that really goes to the classical stable homotopy category. Of course, there's a prime on the right-hand side as well. So if we invert tau, so if we view as tau as a parameter, so this is saying that the generic fiber of this deformation is really the stable homotopy category. So another thing we can do is that since this tau is really mapped between completed spheres, we can just take the co-fiber. We can just mod out by tau. That's a two-cell complex, the co-fiber of tau. So Adamson, by observing that the corresponding Motivic Adams-Novikov spectral sequence collapses for degree reasons, and he established this striking result that the bigraded Motivic homotopy groups of this two-cell complex can be completely written down in terms of homological algebra. So let me emphasize that classically this is never the case. So we don't have anything to say about any finite spectrum, the homotopy groups of the finite spectrum, and completely unless it is trivial for some reason. So the sphere is one example because there's only one cell. But schematically, this object, this two-cell complex, the homotopy groups can be completely described. So following this observation, so Gregory, Wang, and myself, we proved that if you work on the cellular modules over this two-cell complex, so Gregory proved that this ring is actually infinity, then it is actually, the whole category is actually how this unbounded derived category of BP star BP comodules that are concentrated in even degrees. So in the deformation point of view, so after we announced the proof, so we have alternative proofs by Krauss and Pistrogovsky. So this result can be viewed that from the deformation point of view, the special fiber is actually purely algebraic. It's just a derived category of some abelian category, which we understand very well. So this deformation identifies the generic fiber as a classical stable homotopy category, and a special fiber as certain abelian category, which are familiar to chromatic homotopy series. So this deformation actually is very useful in computation because this deformation connects this thing which we understand very well to the stable homotopy category. And so Gregory, Wang, and myself, we proved that this deformation actually gave us an isomorphism of spectral sequences. So Dan Adamson proved that the two abutments are isomorphic. One is this two-cell complex with the bigraded homotopy groups. One is this just the classical Adams-Novikov B2 page. So earlier I mentioned there's the algebraic Novikov spectral sequence converts to here. And we also have a Motivic Adams spectral sequence converts to the two-cell complex. So in fact, this is how the business started. So Dan Adamson, when he earlier computed C-Motivic stable stems, he was just using the naturality of the Beatty realization and compare with the classical stable stems. And he actually also considered this two-cell complex, and he knows this computation up to stem 59. And on the other hand side, so Gordon Wang made a computer program and compute this purely algebraic spectral sequence up to a range, I think at 45 at that point. And when we compare these two spectral sequences, so we know they converge to the same thing, but we didn't expect the whole spectral sequences are actually isomorphic in that range because they're both trigraded spectral sequences. And I showed you a picture earlier, they're actually quite complicated. So therefore, there's no way these two spectral sequences only are isomorphic in range, they must be isomorphic up to infinity. So that motivates us to think these two spectral sequences are actually isomorphic. And since BP star is really the unit object in the derived category of BP star BP comodules, and this is the unit object in the modules over that, so that motivates us to have this conjecture that the two categories are actually equivalent. And later we prove that using higher algebra and by defining a T structure. I'll say a little bit more about that later. So right now, let me explain like why this isomorphism of spectral sequences actually is very helpful in computing stable stems. Well, earlier on I mentioned that so in Miller square, the lower two spectral sequences are purely algebraic, the upper two are much harder to compute with for their differentials. And Miller have this technique that can deduce algebraic Adams D2 differentials in here from purely algebraic data. So now through the Motivic board, we can reprove this and actually generalize this result. And here is how it goes. So the idea here is to use the deformation I mentioned earlier, but through spectral sequences. So these two objects, they live in two different categories, but since the categories are the same, so the spectral sequences are actually isomorphic. So this is the information about this spectral fiber, which is purely algebraic. So that's why we can make a computer program to compute any differentials within any reasonable range. And then the lower two arrows are the deformation I'm talking about. So this is the spectral fiber, this is the whole thing, and this is the generic fiber, which is the Betty realization. When we invert tau, we actually get back to the classical information. So therefore, through the Motivic work and by naturality of some zigzag, we can actually deduce differential from purely computer program output to a classical Adams differential. And if we keep track of the length, we'll see that if we start with a D2 differential, we'll in the end get us a D2 differential. But in general, a DR differential could give us a shorter differential that depends on the algebra in that bi-degree or tri-degree. So this deformation point of view is really helpful in computing classical stems, stable stems through the C-Motivic work. Okay, so this is exactly how we proceed the classical computation. We're going to use computer programs to compute X over C. We're going to use computer programs in the purely algebraic category, compute all the differentials in the algebraic Novikov spectral sequence. And that's the same as the Motivic Adams for this covariant tau objects, which is a two-cell complex. Then we run the covariant sequence for tau. We put back differentials to the Motivic sphere, and we also apply all kinds of R-help arguments such as shuffling total brackets. And in the end, the last step to get to the classical stable stems is simply by inverting tau, and it goes to the generic fiber. Okay, so well, now we have a few questions in mind. So can this covariant tau method be applied to other fields? Because this is kind of specific to C due to the Beatty realization and due to the deformation point of view. And one difficulty would be this element tau does not exist, at least as a map between spheres over a general field. So if we have such a method, what's going to be the replacement for the covariant tau over other fields? Another thing is that, so this is purely based on the cellular part of the Motivic Homotopy category, which is less interesting to algebraic geometers, I guess. What about the non-cellular part? Can this method somehow be extended to the non-cellular part of the category? So in recent work of Tom Bachman, Hannah Jia Kong, and Gordon Wang, so we have answers to these questions. So the idea here is that we define a T structure on the whole stable homotopy category over its field K. So this is actually how we prove that that deformation spectral fiber being algebraic in the first place. We define a T structure on it, and we prove the equivalence as stable infinity categories, but preserves the T structure. Then we identify the heart, and we do some other work. So now we think we can extend this T structure, which we call the Chow T structure, on the whole category. So here is how it goes. So we start with for any smooth proper scheme over Kx and any virtual vector bundle over X. So this is our notation for its Tom spectrum. So the Chow T structure is defined simply by the following. So we say the positive part is generated by all Tom spectrum under colimits and extensions. And the negative part of this T structure are just objects such that anything the positive maps trivially into such an object. So by the general construction, say Jacob Lurie's work, this will always define a T structure. So the point here is that the positive part are generated by this Tom spectrum over a smooth proper scheme over K. So the first interesting observation of this Chow T structure is that it plays very well with the algebraic cobordism MGL. And due to our knowledge on MGL, so for the rest of this talk, we're going to implicitly invert the exponential characteristic of this field K. So MGL is the algebraic volume spectrum. So by work of Hopkins, Morel, and Levine, so we know that its homotopy groups, bi-graded homotopy groups, is actually concentrated in non-negative Chow degrees. Oh, I should mention that Chow degree here means that the topological stem, the first grading, the minus twice of the second grading. So the first grading minus twice of the second grading. So that's our definition for the Chow degrees. So, so MGL is always concentrated in non-negative Chow degrees. And in Chow degree 0, it is actually the Lazard ring. So the Chow T structure plays very well with MGL. So first of all, if we have something in the positive part, which are generated by Thom spectrum, and then by Thom isomorphism, essentially the MGL homology of it is again concentrated in non-negative Chow degrees. So that's not a surprise, but a little bit more of a surprise is that if you take some object in the negative part and we want to compute its MGL homology. So since MGL, just as in the classical complex cobordism case, it can be written as a co-limit of the Thom spectrum over the Gross-Mannings, and it can be rewritten this way. And now, since this Thom spectrum over Gross-Mannings can be dualized, so therefore we can move from the right-hand side to the left-hand side, and that's another way of writing it. And therefore, you can view that these groups are always 0 if the star is in non-negative Chow degrees. So that means if you take some element in the negative part of this Chow T structure, MGL homology is also going to be concentrated in negative Chow degrees. And if we intersect two of them, the bigger equals to 0 and the smaller r equals 0, that tells us anything in the heart of this T structure will be its MGL homology is going to be concentrated in Chow degree 0. In other words, smashing with MGL will be compatible with this Chow T structure we defined.
Really, excuse me, there's a related question in the chat, if you can take a look at that.
Ah, yes.
So it asks about the abelian category of the T structure.
Great question. So I'm going to answer that. The question is, what is the heart, right? What does the heart looks like? So we're going to have two descriptions for it. One is more explicit than the other one in a few slides. Okay, so all right. So to get to the heart question, let me also fix a few notations. So we have the truncation for any object in this category, and that's going to leave in a shift of the heart. So first, crucial theorem, Bachmann, Kohn, Wang, and myself proved is the following. For any object in the stable homotopy category over K, Motivic stable homotopy category over K, doesn't have to be cellular necessarily. And the truncation, it's bi-graded homotopy groups. We can describe it completely in terms of its MGL homology. So here, note that if you take the MGL 2 star star MGL, so that half algebroid by work of Spitzberg is the same as the classical MU star MU half algebroid. So therefore, this thing is going to be a comodule over MU star MU. So this expression makes sense. So in fact, the bi-graded homotopy groups can have this explicit description in terms of its MGL homology. So note that tau does not exist as map of between spheres over general field K. So therefore, if we take the sphere and we take its truncation in the Chow heart, so this object will be our object that plays the same role as the covariance of tau over C. But a few comments here first. So first of all, this is an integral object. So the C over C, this two-cell complex is, we have a two-cell complex at each prime P. But now we have an integral object. So this object is not going to be cellular in any sense. But if we over C, if we complete it at a prime and do some cellular approximation, cellularization, then it will give us this two-cell complex over C. But now we have an integral object over C as well. And recall that over C, then Isaacson proved that the covariance of tau homotopy groups can be completely described over here. And in our case, for arbitrary field K, if we put E equals to 1, the sphere spectrum, and I equals 0, so this is the Chow degree 0 part of MGL star star, which is just MU star. So over C, we have an integral object whose homotopy groups is going to be X over MU star MU. And if we do a P completion, that gives us the P primary part of that for each primes. So in that sense, this is also a generalization of the situation over C, but this is more general. So for any truncation of any spectrum in this Chow T structure at any Chow degree, and we have a description of its bigraded homotopy groups. So then I'd like to get to the description of the Chow heart. We can consider modules over this object. So this is a sphere truncated in the Chow heart. So this is our analog of the Computational Tower object. So the modules over that will inherit a T structure, the Chow T structure. And also we can do the similar thing for MGL and truncate it in the Chow heart. And I should mention that this category has been studied by Bondako in many of his papers. So this one will also inherit a Chow T structure, and because it plays very well with by smashing with MGL. So we have two functors between them, and we have the free functor by smashing with MGL, and we also have the underlying forgetful functor. So this will give us a co-monad. So the first of all, part of theorem says that if we first start with this MGL 6 0 modules over that, and we look at the heart, this can be described as a functor category that preserves all the finite coproducts from PM, the pure motifs over MGL, to the category of abelian groups. And the Chow heart on the whole category will be the same as the heart on the whole modules over this Computational Tower object. And the first description we give is that it's going to be comodules over this comonad C, which is given above. And then we also identify the modules over Computational Tower as a purely algebraic category. They correspond to the derived category or stable modules over this comonad. So if we restrict to cellular subcategories, which are things I'm much more familiar with, and if we restrict to cellular objects, the first result is just going to be MU star modules, which are concentrated in even degrees. So over C, this object will be MGL modeled by tau, and it's already known that modules over that, the cellular subcategory are just MU star modules. Now, actually, the whole category, if we remove the heart, is just going to be the derived category of that. And the whole cellular heart is going to be MU star MU comodules that concentrate in even degrees. And here's another interesting observation, which is that this result here has nothing to do with the base field. So for any base field, keep in mind that we're inverting the characteristic here, and this result is independent of the base field. So Tom Bachman has thought a lot about the base change. If you have questions like that, you should probably check with him. But this is, to us, is kind of a very surprising result, because this result does not depend on which field it is. The heart on the cellular category is always MU star MU comodules. And moreover, this analog of the Computational Tower modules cellularly is again going to be the always unbounded derived category of MU star MU comodules that concentrate in even degrees. So this is again purely algebraic. So based on this first description of this PM description, we also have a more concrete description of the heart look like. And for any object in the heart, in the Chow heart, this is for the whole category, it's given by the following data. We have a MU star MU comodule fx that are concentrated in even degrees for every smooth proper variety x. And for any MGL correspondence, we have the MU star linear map, as in the pullback from these two comodules. And they satisfy the following conditions. And in particular, each co-module here, we will have a co-action of the co-modules by mu star mu, and any map makes it compatible. So that's a description of an object in this category. And the morphism in this category are just the natural thing you expect. These are the compatible maps, makes things commutes in the corresponding category. So, okay. All right. So next, I'd like to explain that this method, these structural theorems can actually help for computations. So if we start with anything in the heart, which doesn't have to be cellular, but in practice, when we compute things, we would still like to, when we run an Adams type computation, we will still like to do a p-completion of sorts. So this will be a co-module over mu star mu. So the p-completion will be a BP star BP co-module. So the theorem Bachman, Cohn, Wang, and myself proved is that the Motivic Adams-Novikov collapses for anything in the heart. So is this in analog of the C-Motivic case, the Covertel, its own Adams-Novikov collapses. But the Adams does not collapse. The Adams is the algebraic Novikov spare sequence for this BP star BP co-module. Okay, and this whole category, if it's cellular, is again going to be completely algebraic, which is the derived category of BP star BP co-modules. So this is going to be the starting point of our computation. So typically, we have this deformation point of view, but over general field, the situation is going to be more complicated than just a deformation. So what's going to happen is actually we're going to have the whole Postnikov Tower. So if we start with the sphere or some completion of the sphere, we can use the Chow T structure to truncate them into a few pieces. And each piece is, so this truncation is based on it's compatible with its MGL homology, by the way. And since its MGL homology is constantly, well, I guess there are several ways to see this thing itself is already constantly bigger or equal to 0. And each piece here will be in the heart up to a shift. So in particular, its MGR or BPGR homology will just be the Chow degree n part of the BPGR star star for these gadgets. And as I mentioned earlier, we actually know their homotopy groups. Their homotopy groups can be completely described by their MGR or BPGR homology. So of course, the game here is not, we just piece together all the homotopy groups of each piece to get the whole thing. Why is that? Because if you do that, that's just going to be the Motivic Adams-Novikov spectral sequence. There's nothing more to it. So the problem is, again, how to compute the Adams-Novikov differentials, which is always a hard job to do. And C-Motivically, each piece here will just be Covertel. So each piece here will be identical up to a shift. And that's not how we get to a large range computation. So we did not just compute Adams-Novikov differentials. So we're doing the Adams spectral sequence, and we use the deformation point view. So now what we are going to do is we're going to use the Postnikov Tower for this Chow T structure and combine it with the Motivic Adams spectral sequence. So what we do exactly is that we apply the naturality of the Motivic Adams spectral sequence for the whole towers, for the whole diagram. And the point here is that over cellular categories, each piece here, each layer here is in the Chow heart, and the whole category is purely algebraic. So therefore, the corresponding Motivic Adams spectral sequence will just be a purely algebraic spectral sequence, namely the algebraic Novikov spectral sequence for different Chow degrees of BPGR or MGL. So, so now, so let me run a few examples of how this method works. So over C, we know BPGR is just BP star adding tau freely. So the tau degree of tau is 2, and all the VIs are in Chow degree 0. So that means that in the odd Chow degrees, there's nothing there. And on the even Chow degrees, it's just a shift of BP star. So which tells us up to a cellular approximation, so these layers are either have trivial homotopy groups, or is just the shift of Covertel in that case. So therefore, this whole tower, the whole Postnikov Tower, is nothing but a tau Boxton tower. We have the sphere maps into Covertel. The fiber is the other sphere, the top cell, and we map another copy of Covert Tau, and so forth. And when we apply the Motivic Adams, so this is the purely algebraic data in the spectral fiber, as we talked about earlier, but all the upper things have identical information. So what we did was to pull back the purely algebraic data to the sphere, and then use the Bethe realization, go to the generic fiber, and that computes the classical stable stems. So we're only making use of the bottom line here. But in general, the upper layers could be very different. So things are more complicated than just a deformation. So over R as the prime 2, so we know the homology point is adding rho and tau in these 2 degrees. So rho here is actually an integral map, but we can also complete it at the prime 2. So then we can form a 2-cell complex as the covert of tau. So we can model by rho. And tau does not exist between spheres, but it does exist between covert rhos. So it can be viewed as a self-map over covert rho. And then we can take its cofiber. So this is going to be a 4-cell complex. So this 4-cell complex looks very similar to a generalized Moore spectrum as studied in many cases in chromatic homotopy theory. So we can prove that up to cellular approximation, the analog of covert tau in the R Motivic case is going to be this 4-cell complex. Okay, in particular, its homotopy groups is just going to be X over BP star BP. Okay, so we know a lot about MGR or BPGR over R as the prime 2. So Hucris first did it in the C2 equivalent case for the BPR as in the Landweber's real cobordism spectrum. And then Makil computed the Motivic case over R. So its homotopy groups looks like the following. So we have rho as a free generator, well, of sorts where there are relations, but all the VIs will have some power of tau depending on the congruence of this number, I guess. Looks like that. To satisfy, first of all, a few relations that really looks like, if you're familiar with the equivalent slice square sequence computation, the difference over there. And then, all the taus, they satisfy further relations, which just looks like as in tau itself as an element in this range. So we can just multiply freely. So this is completely computed for BPGR. So now we want to look at the bigraded ring in a different way. We want to look at its Chow degrees. So we can easily read out the lower Chow degrees for this ring. And again, for Chow degree 0, that's BP star. For Chow degree 1, it's going to be something like BP star mod 2 or mod 2, V1, this invariant ideals. I'm running out of time, so let me just say we can read out these rings explicitly, and we're going to see a lot of things like the BP star mod IN showed up very well. And now we can actually realize this spectrum and have explicit description of them as some modules over this covert tau analog objects. And then the point here is that the higher pieces are going to be decided by the Chow degrees, and they actually correspond to different BP star BP modules. And each of them, we can run a computer program to compute in the rangeable range, and then we have many more players in the field that allow us to do naturality and in the end prove for Adams differentials. So in the end, I want to say something about finite fields. So this is finite fields at all primes, and the computation will be at 2. So as a consequences of Billinson, Lichtenbaum, and Bloccado conjectures, and the work of, however, Kelly-Oster on Stemwise algebras, we know the homology of a point, and also Stemwise algebra action. So that gives us the Motivic Adams E2 page. And the BPGR can be also written in terms of things like that, and depending on the congruence of the FQ of this number Q here, and depending on exactly which rate this is. So this is studied extensively by work of Wilson and Wilson-Oster. So in particular, from our point of view, we can read out the Chow degree 1 part of BPGR very easily just from these congruences. It's always going to be BP star mod out to some power of 2, depending on the congruence. So that tells us the first layer we're going to play with, other than Chow degree 0, which is just X over BP star BP, is going to be another spectrum whose Motivic Adams spectral sequence will look exactly the same as some Moore spectrum. And so we get the E2 page, and we use Oscar computed the weight 0 for some stems, depending on the congruences of mod 4. And in particular, there is a differential which when Q congruent to 1 mod 4, there's already two situations. One is 0, one is non-zero. And when Q congruent to 3 mod 4, they have, in the end, there are two possibilities. It boils down to two possibilities, but they couldn't decide in their work. And that explains the difference of the range they had in mind. So now using this Chow T structure and the naturality of Motivic Adams spectral sequences, with just the first layer, we can have a simple proof for these two differentials, and with the same result, of course. And using the Chow degree smaller equals 3 part, we can actually decide the case they couldn't decide, which it turns out this case is also going to be B0. Okay, so that'll be it. Thank you very much.
Okay, thanks a lot, Jolie, for a wonderful talk. Are there any questions?
Polarna, can I have a question, please?
Yes, go ahead, Grisha.
Yeah. Can I ask to return to the, not to the first page, but to the page where you speak about the problem of extensions?
Problems about extensions. You mean classically?
Well, in fact, my question is about what is this problem precisely about?
You're talking about a general extension problem for a spectral sequence.
Exactly, yes.
So when we construct a spectral sequence that we want to compute something, is usually obtained by some kind of a filtration, right? So the infinity page of a spectral sequence only give us the subquotients of the thing we want to compute with. But we still need to piece them together to get things we really compute with. So say, for example, in the extensions, we have a Z mod 2 and another Z mod 2. But the actual answer we want could be Z mod 2 plus Z mod 2 or Z mod 4. That's the extension problem. So that's the part which is not answered by computing these spectral sequences and differentials by themselves. It's something we usually have to solve by other methods.
Yeah, because I suspect this problem is reminiscent to some problems in representation theory of finite dimensional algebras. And I suspect this problem is a wild type problem when, for simplicity, we can, for example, say that any finite abelian group is a direct sum of cyclic groups, but you can't classify short exact sequences. Classification of short exact sequences of finite abelian groups is a wild problem, the so-called of wild type problem. And I think that's the same phenomenon occurs here, but I don't know what's precisely the uncertainty, how do you call uncertainty principle?
Mahowald uncertainty principle.
Uncertainty, but I suspect this is, looks like, wild type problem in representation theory.
So my situation is actually much less complicated than what you're saying, because the answer I'm looking for is usually just something over Z or over ZP, and the infinity page is just a vector space over FP. So it's just a matter of question when we could have extensions like that.
Yeah, but for example, if you restrict yourself to finite abelian groups which are with exponent p to n, even in this case, for n larger than 6, it is a wild type problem. I mean, classification. Yeah, I think this is, well, I can't say anything precisely right now, but I suspect that this is, well, relevant to the same problem in representation theory. That, for example, classification of short exact sequences, say of abelian groups of exponents p to n, is a wild type problem. you can't well, find a reasonable short exact sequence, a collection of short exact sequences such that any other is a direct sum of this from this subcollection. It is a completely wild problem in representation theory.
I see.
Okay,
I didn't know that. Well,
yeah, just in case. Well, I can send, say, you a link. I think there is a paper of Klaus Michel Ringel about that. Okay, and anyway, I think this is more or less, well, look like each other very similarly. Okay, that's the question. Thanks.
I have a question. If you use this, the element eta didn't occur anywhere in your talk, but if you invert eta, we sort of know what's going on. Does that detect anything?
I'm aware of there are many work done in this sequence. I did not do the answer to your question. Sorry about that. Yeah. So Tom Bachman recently have a result with Mike Hopkins on the eta local sphere, eta inverted sphere, I think, over arbitrary field. So yeah, that you may want to talk to him. I'm sure Tom knows everything about the answer to your question, but sorry about that.
But I have a quick question about the structure of the heart.
Yeah.
Just to go over. So say it's built essentially on the category of MGL motives or MGL 2** motives. Is that correct? Is that it sort of starts with that?
It start with PM.
No, I meant the other description.
Here.
There we go.
Yeah.
So for every MGL correspondence, so the X and the Y there, are those supposed to be smooth projective varieties, or what's
yes.
an MGL? Yeah. Okay. So
yes,
you take the category of MGL motives, so to speak, where the built out of smooth projective varieties with maps given by just the cobordism of the product.
Yes.
I assume.
Yes.
And then it seems then on that you have this pre-sheaf of let's see. I see. And then you're just taking comodules, comodule M2*, MU2*, MU comodule. So sheaves of MU2*, MU comodules on that category.
Yes.
Pre-sheaves. Okay, so that's essentially what you've got there. Great.
Yes,
okay,
yeah.
that was my question. I just wanted to clarify. Great. Thank you.
May I ask a question?
Yeah.
Jolie, sorry about that issue in the 20 stem, but have you calculated pi n0 for n bigger than 20 for over finite fields?
Oh, that's a great question. So in fact, so there's some ongoing work with Robert Buckland and Tom Bachman for weight 0 or finite fields. We think we can somehow give a complete description, but it's still under construction, that result. Yes.
So do you think this pattern with it being the sum of pi n and pi n plus 1, the classical stable stems, is true in general, or?
Yeah, we think that's the case, actually.
Oh, wow, that's great. Okay, thanks.
Mm-hmm.
Okay, yeah, have you determined any Motivic Adams differentials over number fields?
That's a great question. So that's certainly something we thought about doing, but we haven't started anything yet. Yes. So do you have suggestions of which number field in particular we should think about? And of course, we're only computing like a prime at a time, I guess.
Yeah, I mean, of course, it would be interesting to look at the rational numbers, or maybe the Gaussian rationals.
Okay, yeah, that makes sense. Yeah, we haven't started thinking of doing that. But I mean, we have thought about doing that, but we haven't started. Thanks.
Okay, great. We still have time for some more questions, if there are any.
Sorry, do you have any published text on this matter? This is my first question. And the second one, did you try to look for a JSON-based structure to make some computations in the heart?
Sorry, could you repeat your first question and second, please?
Well, did you look at any weight structures to compute?
Right. So I think I learned this from Tom Bachman that it's very closely related to the weight work done by Bundako, right? For this MGL sequence 0 part. So I don't know precisely the connection there.
Okay.
Right. So the reason we can do computations is in the end in this category, in this derived category of these comodules, and it especially works well over the cellular case.
Thank you.
Mm-hmm.
Okay, well, I think that concludes the round of questions. So let's thank Julie once again for a wonderful talk.
Thank you.